Hello and welcome. Mr. Johnson here, and in this video we're going to be talking about bonding, specifically covalent bonding, ionic bonding, and metallic bonding. So let's go on and get right into this. So when it comes to bonding, the first question that has to be answered is, what exactly is a chemical bond? Well, chemical bond is really nothing more than just a mutual attraction between an atom's valence shell electrons in order to be able to create new molecules. But that raises another question. Why bond at all? Well, the reason why we see atoms bonding with each other is because bonding of atoms promotes what we refer to as atomic or molecular stability. And it does this by allowing these atoms and these elements to mimic the stability of a noble gas. In other words, we say that they have valency or they have achieved the octet. So it's all about lowering the potential energy of these elements by becoming stable. And the most stable elements we have are noble gases. So that's what they aim towards. So take a look at this example. Okay? Put this into a better perspective. If we look at sodium, it has a configuration 1s2, 2s2, 2p6, 3s1. And if you notice, sodium, if it could end up losing that one electron out there in that 3s1 energy sublevel, then it would do what we refer to as fall back to the configuration of the noble gas neon. In other words, it would have a configuration of 1s2, 2s2, 2p6. And when we look at that highest energy level of energy level 2, notice that there's 2 electrons in the s, 6 electrons in the p, and that gives us 8 electrons total. That is valency, or the octet. And that's what sodium is trying to do. If it has some way to lose that 1 electron in the 3s, then it would become more stable than it currently is. Likewise, if we take a look at something like chlorine, chlorine has a configuration of 1s2, 2s2, 2p6, 3s2, 3p5. And again, notice in that highest energy level 3, there's 2 electrons in the s, 5 within the p, for a total of 7 valence electrons, which means chlorine, if it could gain 1 more electron, it would end up having the same configuration as the noble gas argon. In other words, 1s2, 2s2, 2p6, 3s2, 3p6. And again, if we look at that highest energy level, notice that there's 2 electrons in the s, 6 electrons in the p, for a total of 8 electrons in that highest energy level. And again, that's what we'd refer to as valency, or the octet. So if I have sodium and chlorine and I put them together, the question becomes, what are these going to do? Because, again, sodium wants to lose an electron, chlorine wants to gain. So what do? They bond. But then that raises another question. What type of bond are they going to end up forming? So for that, we need to look at the 3 different types of bonds. So the first type of bond that we have is what's referred to as a covalent bond. And this is a bond that's formed through the sharing of 1 or more valence electrons. That's the only way for the atoms within that compound to all achieve valency, or to all achieve the octet. They have to end up sharing. The second type of bond is that of an ionic bond. And this is a bond that's formed from the electrical charge attraction between 2 oppositely charged atoms due to the transfer of 1 or more valence electrons. So in other words, you've got something that wants to lose electrons, something that wants to gain, kind of like the sodium and the chlorine. So in transferring electrons, you get charges, and then those opposite charges attract. That forms an ionic bond. The third type of bonding, this is what's referred to as a metallic bond. And metallic bonds are formed through the movement of what we refer to as delocalized electrons within metal atoms. If you think about a sheet of copper or steel or iron or aluminum, what keeps those atoms together? That's metallic bonding. So when we look at these 3 different types, covalent, ionic, and metallic, covalent and ionic are between two different types of atoms. Okay. Now, understand, with covalent, you can have two of the same type of atoms. For example, oxygen molecule, it's two oxygens covalently bonded to each other. Hydrogen, covalently bonded together to form H2. And there are examples of covalent bonding where it's two or more of the same type of atoms. Ionic bonding, it's two or more different types of atoms. And then metallic bonding, it's atoms of the same type of metal. Okay, just to kind of clarify. So let's break this down and look at each type of bond individually. We're going to start out with this idea of covalent bonding. So again, a covalent bond forms through the sharing of one or more valence electrons. So let's take a look at this. We're going to use the example of CH4 or methane. And if I look at the electron configurations for these two different types of elements, carbon and then hydrogen, notice that carbon is 1s2, 2s2, 2p2, which means currently in its highest energy level of energy level 2, it only has 4 valence electrons. So it needs to somehow gain 4 more electrons to achieve valency. Well, I have 4 hydrogens, and each hydrogen has 1 valent electron. So the idea here is that if hydrogen could either give or share these electrons, I drew my arrows to the wrong spots, sorry for that. Let me go back and fix that real quickly. If they can share, they're going to share into the 2p orbital, because that 2s is already filled up. So if they can share or simply transfer electrons into that 2p, then carbon would end up having its 4 additional electrons and have valency. But each hydrogen doesn't want to give up its 1 electron, because hydrogen wants to have 2 valence electrons so they can have the noble gas configuration of helium. So the better idea is for hydrogen to share its 1 electron. Each hydrogen share its 1 electron with carbon, but then carbon also share its 4 electrons between these 4 hydrogens. And when that happens, this is what you get. Notice that in this diagram, the red dots are your electrons from hydrogen. So I've got 4 red dots. That's the 1 electron from each of the 4 hydrogens. And then carbon, 4 blue dots. That is the 2 electrons from the 2s, the 2 electrons from the 2p. And by sharing those electrons, I produce a covalent bond. And when I look, each hydrogen has its 2 electrons to give it the configuration of neon, and carbon has its 2, 4, 6, 8 to have its valency in a configuration that mimics that of neon. So this is covalent. It's a sharing of electrons so that every element within that compound ends up having valency. Okay? But here's the other issue with covalent bonds. We can actually get 2 types of molecules that result from covalent bonding. The first of these is what's referred to as a non-polar molecule. And in this type of molecule, I have an equal sharing or an equal distribution of electrons. In order to have an equal distribution of electrons, we typically have an electronegativity difference that ranges from 0, which means there's no desire for one atom to have a stronger pull on the electrons than the other atom, to a minimal desire of 0.3. So if you're not sure about electronegativities, I highly recommend you go back and watch the video that I made previously on periodic trends, and I discussed electronegativity in that, what electronegativity is, and how we measure it, and what the trend is as you go across the periodic table and down through a column. So there's a little plug for a previous video of mine if you need to know about electronegativity. But anyway, back to nonpolar. Okay? It's an equal distribution, which means one atom does not have a stronger pull on the electrons within that bond than the other atom. So it's nonpolar. The second type is what's called a polar molecule. And this is where you have an unequal distribution of electrons within a molecule. And because one atom has a stronger pull or a higher electronegativity than the other atom, that higher electronegativity atom is able to pull electrons towards itself. And what that does is it creates one end of that molecule, or one pole, that is positive because the electrons are pulled away from it. And we denote that with a lowercase delta and then a plus sign, so delta plus. And the other end of that molecule, or the other pole, is going to be where the electrons are pulled towards, and that's where you have a higher concentration of electrons, and therefore you have a negative pole, which we indicate with a delta negative. And again, how do we get a polar molecule? Well, a difference in electronegativity. And if that difference ranges from 0.3 to 1.7, you're going to have a polar molecule. Now, key thing in this, if I've got an electronegativity difference of 0.3, that is not a very polar molecule. One atom has a stronger pull for the electrons than the other, but not too much of a stronger pull. Whereas if I move over to 1.7, this means the larger the electronegativity difference, the more polar that molecule. So with an electronegativity difference of 1.7, what I find is that one atom has a much stronger pull for the electrons than the other atom. So this is kind of a spectrum of polarity, from low polarity to high polarity. So let's look at this within molecules. So we're going to look at the example of carbon dioxide, or CO2. And when I look at this diagram, and it's showing orbitals based on the Bohr model, okay, what we notice is that there's a nice equal distribution of electrons throughout this entire molecule. So this molecule on whole will be a non-polar molecule. Now, let me explain something else to you real quick. If I compare the electronegativities of carbon to oxygen, we will find that the electronegativity difference is enough to make this a polar bond. But I'm also going to have a polar bond over on the oxygen side. And what we can do for this is we can draw these arrows in, where the plus side arrow indicates my positive pole. So I'd have a positive pole here, my negative poles towards the oxygen. And the idea on this, whenever we look at it, is that those two poles are equal but opposite. So even though I have polar bonds, I end up having a non-polar molecule because I've got equal but opposite poles, and those two poles in essence cancel each other out to give me no polarity. Okay, so please understand that there is a difference between a polar bond and a polar molecule. So this has polar bonds, but it produces a non-polar covalent bond overall throughout that molecule. Okay. As far as polar, again, let's take a look at water. Probably one of the most important polar molecules in all of life. Because in this, oxygen and hydrogen, when you compare their electronegativity difference, this is going to give you a polar bond. And you can notice that all the electrons are pretty much gathered over here by the oxygen. So as a result, what we would do is again put our delta positives by the positive pole and our delta negative by the negative pole. Okay? Another way that you'll see this sometimes in the bonds is they will again draw in these arrows where the plus side of it is your positive pole, and then the head of the arrow, that is your negative pole. Okay? So that is a polar bond. So the next type of bond that we can have, this is your ionic. Again, an ionic bond, this forms from the electrical charge attraction between two oppositely charged atoms. And how do we get two oppositely charged atoms? We transfer one or more valence electrons. So when we transfer, there's two more terms that you need to know. The first of these is what's referred to as a cation. And a cation is simply a positive ion that's produced when a metallic element loses one or more electrons. So if I'm looking back at that example of sodium, that being a metallic atom or metallic element, it wants to lose that electron. So when it loses that electron, I end up with more protons in the nucleus than I have electrons surrounding that nucleus. So I end up with a positive charge, and we refer to that as a cation. Whenever I gain an electron, that's when you have what's called an anion. This is a negative ion that's produced when a non-metallic element gains one or more electrons. So if I go back to chlorine, chlorine is a non-metallic element, and it's going to want to gain that electron. And when it does, now I'm going to have more electrons surrounding the nucleus than what I have protons in the nucleus. So as a result, I get a negative charge. So it is that ionic bond that ends up resulting due to the attraction between that positive charge, that positively charged cation, and the negatively charged anion. And the easiest way to remember that the cation is the positive ion is think about the T within that term cation and think about it as being a plus sign. It's the easiest way to remember that a cation is your positive ion. So let's take a look at how this looks when we're talking about a molecule. So here's this example again of sodium chloride. So notice this red dot, that red electron, that's that 3s1 electron that sodium was wanting to get rid of. When I look at chlorine, there's that void. If I look at its configuration, 1s2, 2s2, 2p, I've got 6 total, 3s2, 3p2, 4, 5, it needs one more. So as a result, sodium being metallic is going to lose that electron over to chlorine, or it's going to transfer. Chlorine gains that electron, and now what happens is notice sodium, 1s2, 2s2, 2p, 2, 4, 6. This has the configuration again of neon, noble gas. But again, I'm going to have more protons than I have electrons, so I get this positive charge. Chlorine, when it gains that electron, 1s2, 2s2, 2p2, 4, 6, 3s2, 3p2, 4, 6. Now, it has a configuration of argon, but because I've got more electrons than what I have protons, I get a negative charge. And it's that attraction between the positive and negative charge that produces that ionic bond, that attractive force between two oppositely charged ions. So that is an ionic bond. Some key points about this, though. These molecules, when you have ionic bonds, they typically are going to have an electronegativity difference that is greater than 1.7. They've got a very large electronegativity difference. Also, this type of bond is usually weaker than covalent bonds. And the reason being is that when we think about an ionic bond, it's simply based on an attractive force. But if we're dealing with a covalent bond, if you're going to share electrons, then you have to have overlap of those electron clouds. And when you have an overlap of electron clouds, that produces a much stronger bonding force than what you have when it's simply an attractive force. Okay? So covalent bonds typically going to be much stronger than your ionic bonds. Okay? So this now brings up the question, how do we know whether a covalent bond or an ionic bond is going to form? Well, as I've already been talking about, we have to look at the difference between electronegativities. Okay? But in general, typically, compounds composed of a metal and a nonmetal, those are going to tend to have ionic bonds because that's where you have the largest difference in electronegativities. Conversely, typically, compounds composed of two nonmetals tend to have covalent bonds due to small electronegativity differences. It's going to be easier for those two nonmetals to share. As far as will a metal bond with a metal? No. Metals want to lose electrons. That's their easiest path to achieving valency. So if I try to take two metals, say sodium and magnesium, both are wanting to lose. They're not going to want to transfer between each other. They're not going to end up wanting to gain electrons from one or the other element. So typically, compounds composed of two nonmetals tend to have covalent. Compounds composed of metal and nonmetal tend to have ionic. And again, we look at electronegativities. Okay? The other idea this is the larger the electronegativity difference, the more polar that particular compound is going to be. Just like I was pointing out, if the difference is 0.3, it's polar but not very much. 1.7, a very polar molecule. So take a look at this table of electronegativities and think for a moment, what would happen, what type of bond would form if I combine, say, lithium with chlorine? Is that going to be ionic or is that going to be covalent? Well, if we look at the electronegativity difference, 1 minus 3 or even 3 minus 1, because you would take the absolute value if it comes out negative, I would have an electronegativity difference of 2. Well, that tells me it's going to be an ionic bond. But again, we could then say, well, I've got lithium as a metal, chlorine as a nonmetal. Stands to reason there's going to be a large electronegativity difference, so therefore ionic. Compare if I take carbon to oxygen, 2.5 to 3.5. Well, that's just an electronegativity difference of 1. That means I'm going to have a polar bond. If I look at nitrogen to oxygen, 3.0 and 3.5, electronegativity difference of 0.5. It's also polar, but that bond between nitrogen and oxygen is going to be more polar than the bond between carbon and oxygen because, I said that backwards. It's going to be less polar because it's got a smaller difference than the bond electronegativity difference between carbon and oxygen. Okay, so again, we can use electronegativities not just to tell us is it ionic or covalent, but if it's covalent, what type of covalent, polar or nonpolar, and the extent of the polarity. So this lastly brings up the idea of metallic bonding. And this is, again, what we have when we're talking about metals, copper, aluminum, etc., and these atoms sitting right next to each other. And this is formed through the movement of what we refer to as delocalized electrons. So the idea on this is that metals tend to have very, very few valence shell electrons. That's why it's easier for them to lose electrons to achieve valency than it is for them to try to gain electrons. Okay? But because they have so few valence shell electrons, those electrons tend to be what we refer to as highly mobile. And because they're highly mobile, when I've got these atoms sitting next to each other, they can easily travel from one atom to other adjacent atoms. Okay? That moving field of electrons, we refer to that as the sea of electrons. And as such, we talk about the electrons as being delocalized. In other words, they can roam from atom to atom. So metallic bonding, it's all about delocalized electrons and those electrons flowing between one atom of that metal and the next atom of that metal. And as a result, as those electrons are moving between them in that sea of electrons, we get attractive forces because as they move from one atom to the other, you get a small little polarity of sorts where one is losing the electron for just a brief moment, becoming kind of negatively charged, the other atom positively charged, and you get that attractive force similar to ionic, but not as strong. Okay, so we've got these moving electrons, and this is showing kind of a piece of metal. All those positives are your nuclei, your protons in the nucleus, and you've got these electrons that are able to easily move through this. This is why metals tend to be such good conductors of electricity. They've got these free-flowing electrons that allows for conduction. Okay? So that is ionic, covalent, and metallic bonding. If you have any questions or you have ideas for future videos, please leave them in the comments. I would love to hear from you. Love to get ideas for future videos. Hopefully this has been a help to you. Appreciate you joining me. Thanks. Take care.